Well, welcome everyone to the afternoon session of today's conference. The first speaker is Clara Aldana. She'll speak about Polygon formulas for conical singularities in dimension 2.
Okay, so thank you very much for inviting me to give a talk in this very nice meeting. It has been really very nice, and all talks have been very interesting. So I will talk about Polygon formulas for conical singularities in dimension 2. And so this is joint work with Klaus Kirsten and Julie Rowlett. And it's already in the archive, so one can find it in the archive. Okay, so I will first start talking about the determinant on compact manifolds. So one starts with a compact connected Riemann manifold of dimension n. One has the Laplace operator associated to the metric, and then one has the spectrum of these Laplacian on functions. And so Ray and Singer define the zeta regularized determinant of these Laplace operators. So there are other forms of defining other determinants. And we compare them and everything, but we use only zeta regularized determinant. So for this, we consider the spectral zeta function that is just the trace of this operator. This is the resolvent minus the projection on the kernel to the power of s. And it's just given by this sum over the positive eigenvalues of lambda j to the minus s. This is the spectral zeta function, and it's defined by, for a complex parameter with real part of s bigger than n over 2. So for real part of s bigger than n over 2, this series converges. So using Mellin transform, we have that the spectral zeta function can be written in terms of the trace of the heat operator. In this form, so we have 1 over gamma of s, and then the integral between 0 and infinity of the trace of the heat operator times t to the power s minus 1. And this is the form we are going to use. So here, using the asymptotic expansion for the small t of the heat trace, we can extend this function meromorphically to the complex plane. So here we have this asymptotic expansion that we have seen also earlier today. And we obtain a meromorphic continuation to the complex plane that is regular at s equals 0. And then we can define the determinant of the Laplace operator as the exponential of minus the derivative at 0 of this meromorphic continuation. So this gives us a number that is a global spectral invariant. And this number generalizes the determinant of a positive matrix. So if we start by the product of the eigenvalues, and we take the exponential of the sum of the logarithms, we can see that this equation follows. So formally, we have this, and this is just a form to regularize this infinite product that we will obtain for the eigenvalues. So this is a little bit of motivation and applications. So as I said, the determinant of the Laplacian is a global spectral invariant. The zeta determinant of forms was used to, or is used to define analytic torsion that is equal to Bayer-Master torsion, a topological invariant. It was proved by Chigger and Müller independently. The determinant of the Laplace operator was also used by Oscar Felix and Sarnak to prove compactness of isospectral surfaces. And it seems to see asymmetries because some of its critical points are spaces with high symmetry. And zeta functions are also used in physics to study Casimir effect, Bose-Einstein condensation, and real actions in connection to quantum field theories. So it's just some notation applications to study these things. So Polygon's formula, that is what I'm going to talk about today, for compact small surfaces. Well, I will talk about this one. So this arose in physics, was proved by Polyakov, this formula for quantization of strings, and it also has connection with quantum cosmology. And in conformal geometry, Polyakov's formula relates the determinant of two metrics that are conformal in terms of local geometric quantities that involve the conformal factor. So if we have Mg, a compact Riemannian surface with boundary, and we have H, a conformal transformation of G by a conformal factor phi that is smooth. Then this formula gives a relation between the difference of the log of the determinants. So this will be seen as a quantum anomaly as this right side that has the conformal factor in local forms. So here we have the L2 norm of the gradient of the conformal factor. Here we have this is the Gaussian curvature multiplying the conformal factor integrated over M. Here we have the geodesic curvature of the boundary multiplying the conformal factor integrated over M. And here we have the normal derivative of the conformal factor integrated over M, all these respect to the metric. So this is the Polyakov formula, or what we call the integrated Polyakov formula for these metrics H and G. So as I said, it was first proved by Polyakov, then Alvarez, then Oscar Phillips and Sarnak, and there are other versions for other cases. So for the variational Polyakov formula for compact smooth surfaces, well, if you have a question, please, or need time to read something else, please tell me. I go too fast. So the variational Polyakov formula for compact smooth surfaces. So this is how we are going to obtain this formula. So we first prove the variational Polyakov formula, and then one integrates this formula to obtain Polyakov formula. So this consists mostly just taking, so this, we start with a variational principle. So we take the conformal transformation of G, that is H, and then we vary in the direction of another conformal factor psi. So we take a directional derivative, that is exactly this. This is called the variation of log of the determinant of delta H in the direction of the function psi. And this is just differentiating this log of the determinants. So this is done by differentiating the spectral zeta functions associated to this matrix H. And then we do several computations that in the compact smooth case are quite simple and very well justified. They don't have any problem. So one obtains this formula, it will be just the finite part at t equals 0 of the trace of this operator that is multiplication of 2 psi times the heat operator associated to H. So this trace has an asymptotic expansion as t goes to 0, similar to asymptotic expansion for the heat trace of a metric. So we are just multiplying by this conformal factor psi. And this finite part t equals 0 is just this constant term. So we obtain this formula. And so this is called the variational Polyakov formula. And to compute it, one needs to know the heat capture of this application of some of the properties of this heat capture. So now, and then one integrates this formula in the direction of these conformal factors, and then one obtains the Polyakov formula in UR. So for surfaces with conical singularities and a smooth boundary, so I will first introduce the definition of these surfaces. We start with a compact two-dimensional topological manifold with boundary and a finite set of points, P1 and Pm, that is contained in the interior of the manifold. So we don't allow conical points at the boundaries. And G is a Riemannian metric on M, so on the interior. And the boundary is smooth. G is smooth on N. Difference these points are going to be the conical points, and each conical point has a neighborhood where the metric is the one of our generalized cone. We write. So this omega I of R is a smooth family of metrics on S1. Then we can also define the angle at the cone using this metric at 0 and integrating just this metric on this one. And what is important here is if we have a metric with conical singularities on M, and we have a conformal transformation of this metric with a conformal factor that is smooth, and in this case smooth up to the boundary and also through the conical points, then the resulting Riemannian manifold is also a surface with conical singularities that has the same cone angles as the original metric. So we don't change the angles by multiplying by a smooth conformal factor. So if we have these conical singularities at this point, we have the Friedrich Laplacian, and the determinant of it is well defined. That follows from the work of several people who have worked with the asymptotics of the heat kernel on and the heat trace on these surfaces. And starting from a variational principle, we obtain this following Polygonal formula. So here we have the metric G, the metric H naught, that is multiplied by a conformal factor into the 2 pi naught. And so the formula here is the same as we had before. So we have the same terms as we had before coming from the interior. And we have the terms coming from the boundary. But in addition, we have for each conical singularity, we have one term. So here we have the sum over the contributions of each point, conical point. So this is the conformal factor evaluated upon pi times these contributions of the angles. And for a surface with conical singularities but without boundary, we don't have the boundary terms, but we have a contribution of the areas. So we have here the areas that come from the, that we don't take the projection of the kernel of. No, we take the projection of the kernel into account. So I should mention that using different methods, Calvin proved a version of this integrated formula that includes conformal factors with logarithmic singularities. So now let me go to curvilinear polygonal domains. So we have a smooth Riemannian surface, and then we have a domain here that is curvilinear. So it has vertices at the, well, the sides are, the edges are just curves. The interior angles of these at the vertices should be between 0 and 2 pi. And thanks to the work of Sultanov, Rowlett, and Scher, we have asymptotic expansion for the heat trace for the Friedrich Laplacian on this curvilinear polygonal domain. It's just the Laplacian on M restricted to the domain. And they also made a microlocal construction of the heat kernel there that allows us to prove the same formula. So thanks to the work, we have this formula for curvilinear polygonal domains on surfaces. So the formula is the same as before, but now we integrate over omega. So we have the contribution again of the interior that is in these two terms, the contribution of the boundaries, and the contributions of the conical or the vertices here. Okay, now I want to tell you about how is changing angles. So for cons. So I start with sectors when we have Euclidean sectors in the Euclidean plane with angles between 0 and 5. So together with Julie Rowlett, we prove a formula for the derivative respect to the angular parameter of minus log of the determinant of the Laplacian on this sector. For that, we use conformal transformations. And as I mentioned, a change in the angle is represented by a conformal transformation with a logarithmic conformal factor. And now we can do the same for cons, and we can consider finite cons. We could follow the same construction we did before, but we can do something else. So let me show you the concepts that we consider are just straight cons with our circle with length alpha. So the conical, the angle is alpha. And now we relate the spectra of cons and sectors. So the spectrum of a cone of opening angle to alpha. So these are going to be given in terms of the end positive zeros of the Bessel function of order absolute value of L, pi, or alpha. So for cons, the spectrum is lambda and L to the power of 2, and L runs over C, and N runs over N. And for a sector, the spectrum is these positive zeros of the Bessel functions to the square, and N and L go only for bigger than 1. So using these, we have the spectral zeta function for cons of opening angle to alpha equals twice the spectral zeta function of a sector of opening angle alpha plus this sum. So these are the zeros of the zero Bessel function to the power minus s. And what we prove is that this part also has an asymptotic meromorphic continuation that is regular at s equals 0, and this gives us this number. So we have this relation for the derivatives of the spectral zeta functions at 0, and this gives us that the derivative respect to the angle of the log of the determinant on a cone at alpha is equal to the derivative of the log of the determinant of the Laplacian on the sector at alpha over 2. So we have this relation for these derivatives. And then using this and the previous formula that I had obtained with Julie, we obtained this formula for the derivative of log of the determinant for the cone. So this formula can also be computed just replacing and calculating these formulas. So this is a very nice formula, I think. And to finish, I don't know how much time I have left.
Well, you started 5 minutes late, so I don't know, 2-3 minutes.
Okay, perfect. So, so to finish, let me show how we can compute the log of the determinant directly from the spectral zeta function using a method of mathematical physics. So the idea here is to do the continuation, the meromorphic continuation, but we are not going to use the heat kernel, but we are going to use another method. So here we have the sector, and then we have the spectrum of the sector that I already mentioned, and then we write the spectral zeta function as this double series of these series of the Bessel functions. And the idea here is we take these series of the Bessel function mu L with mu L pi over alpha, and we use Cauchy's formula to write it as this integral. So this integral over this contour gamma in the complex plane. And the next step consists in deforming this contour to these other contours and taking this limit to 0 here to rewrite this integral, so only this part, as this function. Here we will have sine of pi s over pi, and then here we have this integral. Here we have to go from the real logarithm to the complex logarithm using the principal branch. And here we have not the j function, but the I Bessel function. And for making this meromorphic continuation, then one uses some asymptotic expansion for big values of this order for this I Bessel function. So this is similar to what Kirsten Ward and Kirsten and Doppler have done. And using this method, one obtains this very nice formula for the logarithm of the determinant on sectors. So if you look at this, so this is just a constant. Here we have a term linear in alpha. Here we have this pi over alpha plus alpha over pi. And here we have this function. For this part, we just take away this divergent part. So this converges here. And here this integral converges between. So this is really very easy to compute, and one replaces some values, one obtains numbers that are really, I mean, it's really very easy. It's a very nice formula. And when one differentiates this formula here, one obtains this formula that I wrote here. This is just the derivative of the previous formula. And this formula equals our previous formula that we had obtained before with Julie. So that's that is a bit amazing because they look very different, but they are the same. And I should mention also that Spectral had also found some expression for determinant cones in terms of some series before. And this is everything. Thanks for your attention.
Let's thank Clara for a great talk. Are there any questions? Maybe we have time for like one small question. So what are the stationary metrics with conical singularities besides, the so for smooth, right, we know the constant curvature.
Yeah, for smooth, they are the constant curvature. And for conical singularities,
like if you have some constrained optimization, could it be, constant curvature with conic singularities or something?
Yes. Yes, the idea will be to find which constant metric with conical singularities will give this constraint. And actually, Calvin also has a result about that with spheres. I think he considers a sphere with 2 conical singularities, and then he has some there at the round sphere, normalizing the area, but then one has also to normalize something.
Okay, thank you.
No, thank you. I hope this gave a nice overview on the topic.
Okay, so if there are no other questions, let's thank Clara again.
Yeah, so
Thank you.
thank you.